And then you can start comparing these mock data with your real data. So we have a parameter sampler, we generate mock data, and the mean of comparison is a structure function, first order structure function. A structure function is a representation of the data in forms of variance as a function of time lag. So at a given time lag, you select all the points and you look at the variance of those points. And then you do that for all the time lags. You can bin the time lags logarithmically if you want so. But that is a representation of, if you want so, the variability amplitude or variance at given time lags or given frequencies. And you can do this with your data, and there is a comparison by a summary statistics. We simply define a kind of distance between the structure function, the actually measured structure function, and the simulated structure function. This information is fed back to the parameter sampler, and it will approximate the Bayesian posterior for the parameters that you input. This required major code development. We had at the end to do something like 10 to 20 billion Fourier transforms of significant length. And so we were forced to go to a supercomputer. In this case, we used via the EXCEED environment of the NSF, we used the Comet computer in San Diego and could actually do these computations. So this is how we parameterize the power spectrum at the beginning. So we have here the decorrelation, the main decorrelation of frequency. At lower frequencies at a longer time scale, the process is a white noise process. So if you measure such a star, for example, every day, once a day, it will look like a white noise process. Then in a certain time scale range, the typical one that we observe, you have the correlation. In this case, red noise correlation. And we looked for a possible second break, close where the ISCO is, because it was a prediction for certain models. And we, of course, include white noise. And this is the result. You can very, very nicely fit structure functions. So this is now the structure function of the Spitzer data, and these are the structure function of KEK and VLT. And around that, you see the 1 sigma envelope of our posterior, and you see how nicely our mock data indeed describes the real data. And then you can, from basically the best model, generate a Fourier spectrum power spectrum. So you have a representation in the kind as you're typically used to. It's a very indirect power spectrum, but that is the power spectrum of such a star, and you have a very nicely defined main break. You see here the indication of a second, which is there by construction, but it is not significant within this 1 sigma envelope here. So actually we have not found a second break. And then it goes here into a white noise part. Now this one data set that we had actually common data or simultaneous data between KEK and Spitzer helps us a lot, because we still have some uncertainties in which models to choose. And one of the questions is, what is actually the flux density distribution? Is it a power law? Is it a log normal distribution? And at the beginning we started with a baseline model. In these plots you see here flux density, and here the flux density ratio, or if you want so the spectral index between M and K. And if you take two power laws for 4.5 microns and 2.2 microns, you will find that the likeliest case is a constant spectral index or constant ratio M to K flux over all the flux density range. But we know that it's not true, because we have measured this red point here. So actually what we had to do is we had to force our fitter to obey this additional constraint. I can tell you later in private conversation how you do that technically. And to actually make this happen, we also had to change our model from power law to log normal. So this is a strong indication that actually in the white noise regime, where you cannot quite say anymore, indeed the flux density distribution of the intrinsic variability has a turnover. So if you include this additional information, you come to the following result. Yeah? And this here is now the corner plot of our Bayesian computation, and we have here different parameters. The PSD slope, the main slope of the power spectrum, the second, after the second break, which you can see is not constrained because we are too close to the white noise, but for which we can find an upper limit. Then the main PSD break time scale, which has unprecedented precision now, and we again have a non-constrained second PSD break time scale. However, it's unconstrained because it's so close to the white noise, but it still delivers you an upper limit. So if there would be a signature of the innermost stable orbit, we can say it should be at a frequency higher than 8.5, or at a time scale lower than 8.5 minutes at a higher frequency. Then we have here the flux density parameters for the both log normal distributions in M and K band, and the white noise contributions from the measurement with the three observatories, Keck, NACO, and Spitzer. Now, our best fit model, I have actually made an audio file to demonstrate actually how it sounds. And all the important frequencies now are put into the audible spectrum. So this is a true representation of such a star. And if you see here in this Audacity file, you can see asymmetric. Also, the asymmetry is conserved, and this all gives then the following impression. So you're listening to 4 years in 2 minutes, and it sounds like a scratched record. Actually, that is the sound of such a star following our best model. Well, okay, so this is. I think it was very educative to actually listen to it once. I had never done that before. So about the timescale. So timescale, the characteristic timescale had been estimated before, and you see here in blue the contours of the earlier estimation. And now, especially with our log normal modeling, we can estimate this timescale by a factor of 50 better. So you have here PSD slope versus main break time scale, and you see how much more precise we became with Spitzer data and with our better analysis. You can do more. You can actually now determine a quantity that is called RSVP, rate of stochastic variability power. And this is actually a number that is proportional to the break frequency and to the overall variance of the process. And if you do that for AGN, there is a paper, Kelly et al., who did this for optical light curves of AGN, and they find a correlation of RSVP with the luminosity of the AGN. And if you extrapolate this all the way to the luminosity of such a star, which is, as I said, much under luminous, you end up with a point that is fairly close to this correlation for such a star. It's not quite in there. If this is meaningful, or if this is tracing a more fundamental relation between break time scales and the luminosity, I can not really say. It's just one point and a large, many orders of magnitude that are covered here. But I think it's an interesting point in the comparison with AGN. As I said before, we have an upper limit for the time scale that could relate to the motion at the innermost stable orbit. And with the motion at the innermost stable orbit is a spin estimate possible if you really would have a signature of the ISCO. And for 8.5 minutes, you find a lower limit of the spin of 0.92. Now again, this is with a big caveat that indeed you expect an ISCO signature in your light curve, and the fact that we know now from gravity that it's phase on in sky might actually mean that you don't expect this. So one has to take this with a grain of salt, but this is one of the constraints that we can give from this data. You can also look at the cumulative distribution functions and how well it describes the actual data. And for IRAC, you see that cumulative distribution functions of our best log normal distributions, or the posterior, describe the real data here in black very well. However, for NACO and NUC2, we have flares that are slightly too bright. Not so bright that they could not be described by a chance event and the correlation. So you see it ventures only out into 2 sigma envelopes of the CDF. But it's kind of curious that for both observatories, there are each one flare, these dashed parts of the lines are one flare, which are too bright for the distribution that we fit to the data. So this could be a mild indication that there are indeed very, very bright states that cannot be described with the same kind of variability model. But so far, this is a non-significant event. We can furthermore say that the spectral index changes with flux density, and this is very exciting. So you can do an argument and just say if you have two log normal distributions, and you know in the infrared both wavelengths vary together. That means if one increases, the other increases, and one falls, the other falls. You can actually calculate from your log normal parameters the spectral index variations with flux density. And the argument behind is that you match quantiles. You just say the lowest 10% in 4.5 microns correspond to the lowest 10% in 2.2, and the lowest 40% to the lowest 40%, and so on. If you do this, you have actually an equation with which you can, from the log normal parameters, describe the spectral index as a function of K-band flux density. If you do so, you will find it's a linear function of flux density, of the logarithm of flux density. Now, the interesting thing is that the empirical value for this is only dependent on the sigmas of the log normal distribution, and you will find an empirical value of minus 9.3. Now you can do a physical model, and this is how the statistic now actually will inform radiative models. If you have a model where you say that the infrared part is a optically synchrotron spectrum that at some frequency is truncated exponentially because of synchrotron losses, and this frequency just happens to be the infrared, then you can actually change by going back and forth with this frequency the brightness of the source, but you can also change the spectral index at the same time. And if you really do the math, you will find out it's also a linear function of the logarithm of flux density. In this case, the coefficient here is only dependent on the frequencies at which you determine the spectral index. And although it comes from a completely different direction, this is virtually the same as the one that we just found empirically from the statistical arguments. So I think this is actually a strong indication why you can expect that the energies of the electrons generating this radiation is truncated at a certain point, such that the break-off in the spectrum is not too far away from the infrared. And this has a lot of consequences about the interrelation between the X-rays and the infrared, because there are two schools of thought. One group believes that there is a connection between the infrared and X-rays simply with one synchrotron spectrum. That means we reach very, very high particle energies to also have synchrotron in the X-rays. And other people prefer Comptonization effects, so that you have a synchrotron spectrum into the infrared which breaks off at some point, and you reach the X-rays by synchrotron self-compton, for example. Let me go ahead. So what, as a minimum, we can do here now is we can provide a good characterization of the SED of our variable infrared flux. Before, we had just upper limits, as you remember, but what we can do now for both M-band and K-band, give the quantiles and also give the spectral index as a given state. And so this actually is the proper representation of the infrared variability in terms of the SED. And I hope that this builds indeed a very, very strong constraint for theoretical models. And this is also available if you're interested as a table in the paper. I was told never to show a table in the talk, but I just want to highlight the fact that you just can look at this up in my paper if you need knowledge about the SED in the infrared. Okay, so there are two more results that I just would like to highlight, and they are not really deeply understood yet. One of which is that we measured one continuous Spitzer light curve together with SMA in the submillimeter. And for the submillimeter infrared correlation, there was often discussed the possibility of optical depth effects, so that you have adiabatic expansion or similar models which require the submillimeter to be delayed with respect to the infrared. However, we have here observed one case where I would argue that the X-ray, the infrared Spitzer light curve is followed nicely by the submillimeter light curve, and we have a quasi-synchronous effect. So there seem to be cases where the submillimeter is also optically thin and directly following the infrared. We also have another case. This is not including Spitzer, but comes out of our collaboration, where we have a Chandra data set, again SMA, and then a little bit of Keck data. And this sequence was really troubling because other than expected, we have here a peak that clearly follows the X-ray peak. And for the submillimeter, it's very hard to say if this peak might relate to the infrared or this one. So unfortunately, this has not the required time lengths or time baseline to really do correlation studies. But this is at least very interesting case that illustrates that there might be other sequences between the wavelengths possible that are canonically accepted as being the standard. So in summary, first of all, space-based IR observation with Spitzer, or maybe, hopefully, in the future of James WST, are enabling a more rigorous understanding of the radiation processes at work, both for multi-wavelength campaigns, where you need long baselines to really correlate different peaks, but also to really understand the spectral properties, for example, within the infrared only. We have now really thoroughly characterized the timing of the infrared. This is especially interesting in the context of the fact that it seems to be a blob or a hotspot that is moving in the accretion flow. So what exactly, how are properties of the timing now related to this fact? That is something that in the future I think has to be explained, and is very interesting. And we have several new cases observed between submillimeter and X-ray correlations, and some were very surprising. And we have one more campaign, which are two 24-hour Spitzer and Chandra observations in 2019, and there's campaign information on this page of the Harvard group. So if you're interested to write a proposal and somehow accompany our multi-wavelength campaign, so you're cordially invited. Yeah, thank you very much.
Thank you very much, Gunther. The talk is open to questions. John?
Hi, Gunther. Very nice talk. I have several questions, but let me just fix in one of them. Can you show, I haven't understood properly the relation between the spin and the time scale dependence for the last stable orbit. Could you explain the figure a little bit better? Because I haven't followed you there.
I mean, just a, let me go back first. For a Carrier black hole, there's an equation simply that tells you that the innermost stable orbit for matter, not for photons, is a function of the spin, especially the frequency of it. And so that is what is shown here in the blue curve. So with black hole spin, the ISCO timescale of one rotation around the black hole will decrease. Yeah, and so if you assume that you have such a frequency modulating the light curve, and that is an assumption, but you don't measure this modulation down to 8.5 minutes, it will provide you an upper limit. Yeah. But it's a very indirect, and you know, it really is based on the assumption that you expect a modulation of the ISCO timescale in your light curve. Yeah.
The blue line is the open. Then okay.
This is a measured value that we found. Yeah.
Okay, now.
More questions?
I don't know if this is on. Anyway, okay, so thank you very much for the talk, indeed. And I'm sure you're aware of the EHT collaboration that we are observing every March. And we... have you already? Oh, okay. Okay, that's great news. Just to comment that we do organize a multi-wavelength campaign in coincidence with the EHT observations, and we do have this working group, and I think it would be very interesting if you would be willing to participate. And so.
discussed. Roughly, the problem is that we're not very flexible with Chandra and Spitzer. There are a few Chandra orbits where you can actually do it. They are listed on this webpage. One can really look this up. But I think to really coordinate it, there's a little bit of flexibility potentially from the Chandra-Spitzer allocation side, but not too much. And it's unfortunately to a degree unflexible that it will not allow, for example, gravity and Spitzer and Chandra observations at the same time, but EHT seems to be much more feasible. Yeah, that would be really great. Yeah.
Regarding the submillimeter array and Spitzer correlations about the flare, will you able to detect the flare with both facilities? Could you comment a little more about this?
Understand.
Was detected at the same time with Spitzer and submillimeter array. Yeah. Will you able to do that? At the same time?
This is one of the last slides that we have one data set indeed where we have observed with SMA and Spitzer, so we have sub-millimeter coverage, and in this case indeed it looks like that the variations seem to be somewhat simultaneous. With the error and the noise in it, it's a little bit hard to say exactly how much, and there's still analysis to be done. But it's certainly not a 2-hour delay or something, or 1.5-hour delay, as has been proposed from adiabatic expansion models in this case. So there might be an indication that the relation between submillimeter and infrared is more complex, can be different at times, which would not be so surprising, I guess.
It's not exactly what you've done, but I think you're a good expert to judge on this gravity result, for example. I mean, it's very surprising to have hotspots in the plane of the sky, but they have several measurements, so which gives it a high credibility. Still, it does not align with anything in the galactic center, and if anything, I would expect a completely randomized accretion flow from stellar winds from everywhere. I don't know. Do you have any opinion on that? What we expect
is that we have to wait. That we saw first results, and they are very exciting. And I think the fact that the polarization has a similar signature and time scale as the astrometric signal, that looks very convincing to me. If we are right with the interpretation, that is very simply a phase-on accretion flow with a hotspot, not sure about this. I'm looking very much forward if maybe EHT can give really independent data and an independent analysis. I also hope that there will be more flares observed in this way. It becomes a little bit clearer. It is interesting because at the beginning there was the idea that that hotspots in a most likely not face-on disk would modulate the light curve, and you would find something like a quasi-periodicity, for example. That is actually in the very early times was the biggest excitement about the light curves of such a star, and I think even the starting point of the gravity project. And now, interestingly, you see this one orbit doing a moderate flare that just has one peak, where you don't see submodulations, and it's giving you one revolution. And at the same time, from the statistical analysis, there is not really evidence, in my opinion, for quasi-periodicity or something more deterministic, at least not if you look at the amplitudes. There might be phase correlation for which this kind of analysis is blind to, and one probably has to expand it. So these are now the questions that I'm really interested in. How can you understand those results together? And what the minimum is that you have here now a statistical baseline, and you can insert certain signals that increase and diminish with inclination in the sky, and then ask, at what inclination would you actually be sensitive for something periodic that is caused maybe by boosting or something, and then this would give a further constraint to the inclination, and one could see if this is in agreement with gravity fine. So I think there are a lot of avenues now opening, and I think it needs more thinking. I think it's way too early to say something conclusive there. Yeah.
So thanks again, Gunther.